lecture. Our topic today is the measurement problem in quantum mechanics. And you may or you may not have come across this so far in your quantum mechanics lectures. It's not usually taught in the quantum mechanics lectures, but it's very popular in the popular literature. So if you open a book about the meaning of quantum mechanics or books that discuss quantum mechanics for popular readers, they very often discuss these more philosophical aspects of quantum mechanics, these questions of what is the correct interpretation of the quantum mechanical formalism. You then probably have heard that there are all kinds of interpretations, like many worlds, many minds, relative state, the Copenhagen interpretation, and so on. So that's a somewhat strange situation. In other theories of physics, we do not need such an interpretation, or there is not really much discussion around it. If you think of general relativity, for example, the theory is relatively clear, like what it tells us about nature. We have a space-time that's some four-dimensional manifold. It has curvature. This curvature acts like something that for us feels like gravity. And there really isn't much need to put much interpretation on this. The formalism is relatively self-explanatory. And this is completely different in quantum mechanics. And to understand why that's the case, you first have to realize that quantum mechanics, the way we're doing it today, like the orthodox way of doing quantum mechanics, consists of two parts. So the first part is the mathematical formalism, which is well known, well defined. We have a wave function. Wave function psi for n particles, for example. So it lives in configuration space. For the case of n particles, that would be r to the power of 3n. And we have a Hamiltonian h. And this Hamiltonian gives us the time evolution according to the Schrödinger equation of the state. So we have the Schrödinger equation. And that is basically the dynamics of the field. And then in addition to that, we know that we have observables, which are self-adjoint or Hermitian operators. That can act on these states. Sorry. And so far, that's all mathematically well defined, and we can treat all the dynamics of the theory with that. We can solve the Schrödinger equation for every situation that we want. But now the second part of the quantum mechanical formalism is the part where we connect this mathematics to reality, or to what we actually observe in an experiment. And this bi-law, this second law that comes in addition to the Schrödinger equation, is what we usually call the measurement postulate or projection postulate. And it mainly consists of three steps. So the first postulate, or the first part of this postulate, is that whenever we make a measurement, this measurement corresponds to one of the eigenvalues of our observable, of the operator that we measure. Measurement. So eigenvalue. measure acting on psi lambda times psi. Sorry. We call the eigenstate that corresponds to this operator called lambda. And the second rule, is that whenever we make such a measurement, then we cannot predict with certainty which eigenvalue we will find, but the probability for each eigenvalue is given by what is called Born's rule. So the probability of finding the eigenvalue lambda is given by the projection of psi onto lambda squared. And finally, the third part of it is the so-called collapse postulate, or the collapse of the wave function, which means that after the measurement, the system that is in, say, psi before will then be in the eigenstate lambda that corresponds to the measurement outcome. So those three parts. And this is problematic in three different ways. So the first is that this is a stochastic, a probabilistic process rather than a deterministic one. So quantum mechanics allows us to only predict with which probability we will find a certain eigenvalue, but it does not tell us anything about which of the possible eigenvalues will occur. So this is different than classical mechanics, of course, but it doesn't have to be a problem by itself. But of course, it raises the questions, well, probabilities of what do we have? Like, what are these probabilities telling us? If I tell, well, I have two different eigenvalues, say I can measure spin up and spin down with a probability 1/2, then what does this probability mean? What is it a probability for? The second one is the collapse of the wave function here. And this is a somewhat bigger problem because this process that the state psi just jumps to the state lambda is actually incompatible with the Schrödinger equation. It's incompatible with the linear evolution described by the Schrödinger equation. So the Schrödinger equation does not give us such a process. So there is somehow a second dynamic law that kicks in when we make a measurement that evolves the state in a different way than the Schrödinger equation. So also this by itself does not have to be a problem, right? We can of course have two different dynamic laws. It's not the most beautiful theory, but there is no fundamental reason to reject something like that, as long as we can make a clear distinction in which situations we have to apply which of the two dynamic laws. As long as it's clear, in this situation we need to use Schrödinger equation, and in that situation we need to use the collapse postulate to describe the dynamics. Everything's fine. But that brings us to the third problem, which is that the notion of measurement itself is not really a well-defined one. So the question, what is actually a measurement, and and in which situations do we still have the usual evolution according to the Schrödinger equation, is not one that can be clearly answered. And this demarcation problem, this was most prominently addressed by Bell, and I just cite. Bell writes in a popular article that he wrote, what exactly qualifies some physical system to play the role of measurer? Was the wave function of the world waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? So this is obviously just a way to show how ridiculous it is to somehow claim that our notion of measurement is in some way important for the fundamental laws. So there must be some other type of distinction. And of course, you can always argue that measurements are basically whatever involves macroscopic systems, whereas as long as we have microscopic systems, we do not have these measurements, but this should be part of the laws of quantum mechanics. You should have some clear rule and not in the theory that really tells you, okay, where's this line between microscopic physics, where the Schrödinger equation applies, and the macroscopic physics, where you need this collapse law. So these problems, and especially this last one, are not just a mere philosophical question that requires some interpretation or some philosophical discussion, right? But you see that it actually shows that the theory of quantum mechanics as a fundamental theory is inconsistent. The theory itself does not explain the measurement outcomes. It just gives a rule for all practical purposes, how we calculate probabilities, but it doesn't give the fundamental explanation of this. So the measurement problem is not a philosophical problem, it's a physical inconsistency of the theory that in some way or another needs to be resolved. And so let us address this problem in a slightly more formal way. And this slightly more formal way is that you can write down 3 statements that all 3 by themselves sound reasonable, but you can actually show that they cannot all 3 be true at the same time. The first one is that at any given time, the state vector called psi t, the state vector provides a complete description of a physical system. So this means there are no hidden variables. This is another way to formulate this. Or another way to say this is whenever you have 2 systems that are described by the same state, then they are physically equivalent. If 2 systems are described by the same wave function, they should give you the same physical content, they should give you the same the same outcome for all possible observations. So this is exactly the completeness that Einstein, Podolsky, and Rosen were looking for in their EPR argument that we discussed in the first lecture. So this is one assumption, that the theory is complete. The second one, B, is that the state psi evolves according to a linear equation, like the Schrödinger equation. It doesn't have to be exactly the Schrödinger equation, but it needs to be a linear equation. So linear evolution. And finally, and this is the one that is hardest to express in precise words, but statement C is that measurements have determined outcomes. Yeah, so basically, if we, for example, if you have a photon and a photon detector, and you send it through an interferometer, we have two arms, and you can, with your detector, you can detect in the two arms, is the photon here or is the photon here? Then you will either get a result, there is a photon in this arm, or you will get a result, there is no photon in this arm, and nothing in between. So measurement outcomes are always determined basically in a classical sense. You either find one photon, or you find no photon, and not something unclassical in between. I guess another way to express this would be the fact that we observe that measurement outcomes basically are compatible with our classical picture of the world. So also note that we use the Dirac notation here for the state, but in fact we don't really need Hilbert space vectors here. The psi can basically be an element of any vector space for the arguments here. Also the time evolution here, so we are basically arguing in non-relativistic terms that there is a well-defined time variable and we have a time evolution, so this is in some sense a non-relativistic argument, but nothing fundamental changes about this if you have a relativistic setting. You would just then have to be a bit more precise formulating these statements, so you would need to talk about initial conditions on some hypersurface, and then have an evolution with some time direction. But you can make exactly the same arguments also in a relativistic setting. So this is not a problem that goes away by just going to relativity and talking about quantum field theory instead. You have exactly the same problem with quantum field theory. It's just a bit more complicated to formulate in quantum field theory. And to see why those three statements are incompatible, let me first make some space. So to see the incompatibility of those three statements, let us look at a simple case again, like in the EPR argument before. We look at the spin 1/2 system, which can be in states spin up and spin down. Those are, as usual, is the spin along the z direction. And we can also look at the states plus and minus in the x spaces, which are 1 divided by square root of 2. And then up, plus, minus, down. And in addition to this spin 1/2 state, we have a measurement device, and this measurement device can be in two states that we call up and down. The measurement device can be an arrow pointing up or down, can be some light display or some screen that shows up or down, or some detector attached to a printer that prints the words up or down on a sheet of paper. You can make this arbitrarily complicated. The point is that it's described by those states. Whatever the setting is of your measurement device, that would show you, okay, this is I measured spin up, this contains this state, and correspondingly spin down. So what we will find is that if we have our system in spin up, and our measurement device is in some initial state, which we call the ready state, which could be like if you have a pointer, then being in the middle between the up and down position, for example, or the white sheet of paper that has not been printed on yet. Whatever the measurement device is in before, that's the state ready. And now the evolution, according to the Schrödinger equation of this state, it will evolve during the measurement process. It will evolve into the state up tensor, the state of the measurement device. And the same way for state spin down. So we have those two possible outcomes. This just means if we're in one of the eigenstates of our operator that we want to measure, then we will find this eigenstate with certainty. We find the measurement device pointing to this respective state. But now the linear evolution tells us that if we're in the superposition state, say plus here, plus, the measurement device is in the ready state, then just according to the linear evolution, the linearity of the Schrödinger equation, so our assumption B requires us to conclude that that this state will evolve into the superposition 1 divided by the curve 2. Up, tensor up, plus down, tensor down. So according to our postulate A, this state now should provide a complete description of the system that we find after this measurement. So whatever the physical situation of the world is after we made our measurement of the superposition state should be contained in this state. But you see that in this state, the up and down, for example, enter completely symmetrically. So just from a point of symmetry already, just a symmetry argument would forbid you to say, well, this is now a definite outcome that either points up or points down. This is somehow something in between. It's still a superposition, but now it's a large superposition for our measurement device. This is exactly what we found last time also when we were talking about decoherence. So this result is somehow incompatible with our assumption C, that there is a definite outcome of the measurement in every situation. Yeah, and this is basically the essence of the measurement problem, that we need to get rid of one of those three properties, A, B, C, in order to make sense of quantum mechanics. Quantum mechanics cannot have all three of those. And this now also classifies the possibilities that we have to resolve the measurement outcome. Basically by depending on which of those three properties we give up on. Of course, we could give up more than one of them and still have consistent theory, but such solutions are usually not discussed. What we can do is we can give up the property A. So we say the state is not complete. We allow for something more than the state. And this something more is then usually called hidden variables. So those would be hidden variable theories. And a prominent example, actually only really concrete example of such a hidden variable theory is Bohmian mechanics, which I will briefly talk about after this. The second alternative is we give up B, the linear evolution, the Schrödinger equation. And an example for this, so the class of theories that does this, that tries to resolve the measurement problem by getting rid of the requirement for linear evolution, are called collapse models. sometimes also objective collapse model to make the distinction that this collapse is actually a physical process in these models and not just something subjective that happens in the mind of an observer. What these collapse models do is basically they replace the linear Schrödinger dynamics with a dynamics that has the behavior that for microscopic systems, where we know that quantum mechanics works, it's still, to very good approximation, the well-known dynamics from the Schrödinger equation. But if you go to macroscopic systems, to large systems, as we observe them in the classical world, then a different dynamic kicks in. So there is some transition. The larger the mass becomes, or the larger the size of the system becomes, the more nonlinear becomes the dynamics. And this nonlinear dynamics that takes over then acts in a way that really explains the collapse of the wave function into the different outcomes. And we will talk about this in the next lecture next week. And finally, our last option is to get rid of C. Allow for indeterminate measurement outcomes. So this state that we just had, the superposition state of the device being spin up and spin down, is actually seen as the real state that describes the system, and we just try to deal with this as an explanation of the world. And these types of theories are often called many worlds theories, or also many worlds interpretation. And I will talk about those too. So this is basically the way to stick with the formalism of quantum mechanics, to not change anything about the formalism. So don't add anything to it. Just keep the state as it is, as the complete description. Don't change the dynamics in any way. Just take the formalism as it is, and then try to make sense of it. So in this sense, the many worlds interpretation is kind of the only interpretation of quantum mechanics. It is not a interpretation, it's the interpretation. So if you think that the formalism is fundamentally right, doesn't need to be modified in any way, nothing needs to be added to it, nothing needs to be changed about the dynamics, then many worlds is what you kind of almost unavoidably end up with if you're being honest and don't just refuse to talk about the problem altogether. So one thing that I should maybe mention is that for our criteria A, right, we said that the state vector gives a complete description of physical reality. And of course, this kind of implies the existence of physical reality at all, that there is even somehow a real world that is described by these mathematical states. So we talked about this in the first lecture in connection with the UPR argument, and also about the consequences if you would give up this idea of reality, of some physical reality. But just for the sake of completeness, there are some people who basically claim that the solution of the measurement problem is exactly to get rid of this reality assumption and to take some sort of agnostic view about the physical meaning of this state. So, as I said, the first solution, the solution to solve the measurement problem by adding something to quantum mechanics is Bohmian mechanics. Bohmian mechanics is the most prominent example of an hidden variable theory. And the thing that Bohmian mechanics adds to quantum mechanics are particles. Particles that have concrete positions. And their dynamics, their motion in space is determined by the wave function, which acts as a guiding field. So we have the wave function. Generally, depending on time and particle coordinates. function solves the Schrödinger equation. So have my h bar d psi by dt equals h psi. And yes, plays the role of a guiding field, guiding wave. But now, in addition to this, we have n particles, which are particle coordinates. Yes, Q1 to Qn. Those are the particles, and they satisfy a second differential equation called the guiding equation, which reads the following way. The time derivative of the position qi as a function of t, so the trajectory of the ith particle is given by h bar divided by the mass of that particle, and it's the gradient with respect to the position xi of the ith particle of the imaginary part of the logarithm of the wave function. And this derivative evaluated at the position of the particles. So x1 equals q1, and so on to xn equals qn. So you see this is a quite complicated equation, but the fact is that those two equations together, the Schrödinger equation for the wave function psi, and this guiding equation for the motion of particles, those two together actually give you exactly the same predictions as quantum mechanics does. So the randomness that you find in quantum mechanics is then reduced to the initial conditions that you choose. So you have to choose an initial wave function. So the initial conditions are that we have a wave function at t equals 0, and we have n particle coordinates at t equals 0. And now you can show that if you choose those initial conditions in a way that is compatible with the Born rule, such that the distribution of, so you have a distribution of these possible initial conditions, right? So these are in some way indeterminate. So you have a stochastic distribution of possible initial conditions, just as in classical mechanics. When you do classical statistic dynamics, you have an uncertainty of what exactly your initial conditions are. And if the initial distribution of those possible positions is compatible with the Born rule, so the probability at time 0 to find the first particle at q1, and so on. So this probability of finding these particle coordinates initially is the absolute value squared of the wave function. So if this applies, then the dynamics gives you the result that this is also true at all later times. So P of t is again the absolute value squared of the wave function. Okay. So in this sense, Bohmian mechanics gives us the Born rule for probabilities of finding certain outcomes as a natural consequence of the dynamics, given you choose the right initial conditions. And and as an example of this, how this works, is like a very famous example is the trajectories in the double slit experiment. So let me show that to you. It's a picture that you can also find in the script. So if you look at the double slit experiment in Bohmian mechanics, and you actually can trace back how these trajectories look like for different initial positions, then you can basically look at, like, depending on where this particle crosses the double slit, it follows these quite curvy trajectories that somehow just reproduce the interference pattern with the probabilities that you know from quantum mechanics. So you can in fact get this interference pattern as a consequence of classical trajectories, but classical trajectories that look somehow chaotic but are deterministically defined basically by the initial conditions that you give. So this brings us, of course, to the question: well, why aren't we using Bohmian mechanics? Why do we still learn the usual interpretation of quantum mechanics in the introductory courses at university? Why isn't everyone working with Bohmian mechanics? So this, for some part, probably has historic reasons. Right? So the orthodox formulation of quantum mechanics, Copenhagen interpretation, just was first. Another reason is that it's mathematically much easier to handle in the situations that are most important, where you really want to make predictions for measurement outcomes. It's just not very practical to have to deal with this complicated equation for particle trajectories. But from a more fundamental perspective, one of the big problems of Bohmian mechanics is the question how to make it compatible with special relativity. So this is a non-relativistic model that works well and reproduces the predictions of quantum mechanics. But if you want to find a relativistic model that would also give you the same prediction as quantum field theory, basically, then you would first of all want to somehow replace the particles with fields. This is something that can be done in principle. Right? You don't have to have particles here. You could also have fields that have some guiding equation that determines how they behave. But to get this done in a relativistic way, in a way that's compatible with special relativity, is quite challenging, and so far no one has really succeeded doing that in a convincing way. So the other point of view is that of many worlds, which is basically trying to keep both the linear evolution of the Schrödinger equation and keep the completeness of the state vector. And then you are forced to take the superposition state that includes the measurement device as the real physical state of that system, the state that corresponds to physical reality. And one thing that helps a bit with interpreting such a state is decoherence, which we learned about last time. So you have, for a full description, you would also have to include the observer as a person into the description of the state. So you don't just have the measurement system in the lab and your spin that you measure, and the spin is up and the measurement device shows up. But in principle, you have to include everything. The whole environment has to be included in that state. So if you want to do that, just the observer, so the person, the experimenter that walks into the lab and reads this device, then you end up, if you take the linearity of quantum mechanics seriously, you end up in a state that would be the following. superposition. On the one hand, you have the state where the spin is up, the device shows up, and this is entangled with an observer that sees and thinks, oh yeah, okay, I measure spin up. And on the other hand, you have the same for spin down. So you have the spin down times the state where your measurement device is down times the observer seeing spin down. So this is kind of the state that you ultimately get. And then we learned last time, if you now apply decoherence, then you would basically end up for all predictions that you would make, you would end up with a classical mixture of these two possibilities. So for all outcomes, you would predict a 50-50 possibility to be either in the one or in the other scenario. So in the picture of the many worlds interpretation, you really have two different branches, those are then called. One in which the spin is up and everything is consistent with the spin up, and one in which the spin is down and everything is consistent with spin down. And after decoherence, those two branches do not interact with each other anymore. They just don't talk to each other anymore. So everything that goes on here now can do further experiments here, but everything here will be consistent with this particular particle being in the spin-up state. And everything here will be consistent with this particular particle being in the spin-down state. So the one question of that is, of course, if you're comfortable from a philosophical point of view to accept this presence of many worlds and yourself kind of being in a superposition of different outcomes, right? So there is a copy of you somewhere that lives a completely different life, that's the more philosophical discussion, which I want to avoid for the purpose of this lecture. The other problem that's more related to physics is the question: so if you have this, then how do you make sense of the Born-Moore probabilities, which are an observed fact, right? If you measure certain experiments, you find that certain things happen with certain probabilities that are given by Born's rules. For example, take the state that we had. So I can just put this here. Take the state that we had. We had 1 over square root 2. Up plus down, so our state plus times the measurement device in the ready state. And we said that this goes to the superposition 1 over square root 2. Now we have this entangled state. But we can also find a different state. We could look at the following superposition, just with a different way. You can write square root of 3 spin up plus spin down. And this state, just as well, will go to a superposition with the same weight. So 1/2 square root of 3 up tensor up plus spin down tensor measurement device in ground state. So in both we have a superposition of the detector being up or the detector being down, but now with different weights. And we know that what the Born rule tells us, that in this case we will observe up and down with 50% probability each, 50-50, whereas in this state we will find a 75% probability for up and a 25% probability for down. So what is the difference between those two if you're in a many-world interpretation? So both of them are somehow a split world in like two branches. There are like two different worlds. One energy has spin up and one energy has spin down. But somehow those appear in a different way. So should you think of this as like there's one branch for the one and three branches for the other? Or should you think of this in a way that to say, well, there are two branches, but somehow I have a 3 times as likely probability to find myself in this branch. So what's the meaning of those coefficients? And one way to think of this that a lot of people choose is basically talking about the frequency, how often a state like this would appear if you would have an infinite ensemble, so an infinite number of copies of our system of spin up and spin down with for example, the square root 3 prefactor. And that then in such an infinite ensemble, the one with spin up occurs more often than the one with spin down, for example. In order to understand that in a bit more detail, first you can think of this type of many worlds interpretation in a way that essentially replaces the postulates of quantum mechanics over 2 of the postulates. So we keep the first 3 postulates of quantum mechanics. Just to reiterate, the postulate 1 of quantum mechanics is that states are described by Hilbert space vectors. The second postulate is the evolution of the Schrödinger equation. The states evolve with the linear Schrödinger equation. The third postulate is that observables are associated with permission operators. And that the only possible outcomes of a measurement are eigenvalues of such operators. So part of Q3. So possible outcomes are eigenvalues. And now in the usual interpretation, the Copenhagen interpretation, we have 2 more postulates. One is the Born rule. That's P4. That if the state of the system is psi, system is in some state psi, then the outcome of measurements, a measurement of the observable A, will give a certain eigenvalue say AI, with a probability for the eigenvalue AI is given by the projection absolute value squared of the eigenstate psi I to this eigenvalue onto the state psi squared. So this is the probability of finding a certain measurement outcome, of finding a certain eigenvalue. And then there is the fifth postulate, which is the collapse postulate or projection postulate. That is that after the measurement, immediately after the measurement, the system will now be in the eigenstate psi I. So basically the measurement makes the system jump from the state psi to psi I, the eigenvalue, the eigenvector corresponding to the outcome. And you can think of this many words interpretation by replacing those two with some new postulate. So we get rid of the collapse and we get rid of the probabilistic outcome, and instead we have a single postulate that is well defined. Call this P4 prime, and P4 prime is if a quantum disk system is described by the eigenstate psi I, so if we're in an eigenstate of the corresponding operator, then a measurement will result in the corresponding eigenvalue. Okay, so this new postulate makes no statements about what happens to states that are not an eigenstate. It only is a statement about the eigenstates. And now the idea, what people try to make sense of this, how people try to make sense of this, is that you look at, instead of looking at your state, you look at an ensemble where you have a large number of copies of that state. So we have a more general version of the state we had before. So say we have our state psi is a superposition of alpha times up plus beta times down with general coefficients, alpha and beta. So it does, of course, for the state to be normalized, we need to have alpha squared plus beta squared equals 1. And now we can look at an ensemble of n copies of this state, which is in the state psi n, which is just the product of the state n times. And for example, look at n equals 2, then if you want to describe the state, the square of the state as a vector, then the elements would be, so if you choose a basis where your first basis element is up, the projection of this on the side, your second element would be down, side, the third basis element is down, up, and the fourth basis element is down, down. Then you find that the elements of this vector are alpha squared, alpha beta, and beta squared. And you can generalize this, so you will generally find sorry, you will find for this, so this is 2 times up, and here you have 1 times up, and here you have 0 times up. So in general, for arbitrary n and for k times the spin up, you will find that you have choose k of n possibilities, which appear with which have a factor here that is alpha to the power of k, beta to the power of n minus k. So this is what the state looks like for general n. And now we can introduce the frequency operator that just counts how often we find the spin up. So we call this operator f up. So f up for the state up would give us 2. For the state up down or down up, it would give us 1 because there's 1 times spin up. For down down, it would give us 0. So in the case of n equals 2, this would, for example, correspond to the diagonal matrix 0, 1, 1, 2. Or in general, it would be a diagonal matrix where you find 0, and then you find the binomial coefficient n above 1 times the 1, and so on. We find several times the 2. And now we can show the following in the limit where n goes to infinity. So we have the state psi infinity, which is just the limit of the state psi n. And for this, you can show that it is actually an eigenstate of this frequency operator. So this operator f up acting on this state psi infinity, then we find psi infinity again, and the eigenvalue of this now is the probability to find spin up, which is of course given. So which is given by the usual Born rule probability. So the projection of spin up on psi absolute value squared. So basically, this is an outcome of the formalism now that this infinity state, this infinite ensemble, is an eigenvector of this frequency operator with an eigenvalue that is exactly the Born rule probability. And now the question is, how do you interpret this? So we can calculate the Born rule probabilities. We don't have to postulate them as in behave in quantum mechanics. We can get rid of our postulate P4, right? So our new postulate, P4 prime, actually tells us, yeah, if we have an eigenstate of some operator, then we know the outcome of this eigenstate. So we know that for the infinite ensemble, this disobservable of the frequency of spin up agrees with the Born rule. So in the case where we can kind of measure it, if we do an infinite number, this is kind of what we need to do in order to make a statement about probabilities. In this case, in this case, the outcome agrees with the Born rule. So this statement is, there's a bit of controversy around whether or not that is meaningful in any way. So some people see this as basically the convincing argument that the many worlds interpretation makes sense. Other people reject this argument. Of course, one thing you can say that we never have an ensemble with infinitely many degrees of freedom. But the other thing is also really like, so you see that you can calculate the Born rule probabilities, but what is the conclusion that you draw from this about the meaning of this? And in order to discuss this a little bit more, let us look at a slightly different example. And let's just go back to the double slit experiment. So, two slits, label 1 and 2, and we have some screen after our double slit, on which we will find the usual interference pattern. So you can say we can assign some state psi1 to the particle going through the one slit, and psi2 to the particle going through the other slit. So after the slit here, we would find the state 1 over square root 2 psi1 plus psi2. This is the superposition of the two possibilities. And we can now look at the two. We can now look at the two projection operators. So we can look at the projection operator psi1. This operator basically gives us the number of particles that we found that went through slit 1. So this is the operator that measures the number of particles through slit 1. And in the same way, we can have the projection operator for the second particle. And now we can define an operator S, which is just the sum of those two projectors. So you can say S counts the total number of particles that went through some slit. Okay, so this is number of particles through either slit 1 or slit 2. And now we can apply this operator to our state, and we find that this is an eigenstate. Okay. I should write it in bracket and in Dirac notation, also up here. So S acting on the state, psi1, psi2, you can just do that yourself. If this projector and this part survives, if this projector and this part survives, so get 1 over square root 2. Psi1 plus psi2. So our superposition state after the slit is an eigenstate of this operator S with eigenvalue 1. So based on the postulate that we had, our P4 phi postulate, we would say that the state for this observable S, this state has the determined measurement outcome 1. So in this sense, we can say we measure that this state goes through exactly one slit. This is just the application of this postulate. And now the question is, from the fact that the particle goes through exactly one slit, can we draw the conclusion from this that the particle must go, because this is just like two equally contributing states to this, can we draw the conclusion that the particle goes through slit 1 and slit 2 each with a 50% probability? So 50%. We have a 50% probability for slit 1. And of course we know that this is not the right way to talk about this, because we observe this interference pattern that is incompatible with this classical interpretation. And this is exactly, this is also the problem essentially with this frequency rule. So you can definitely compute for this large state, for the ensemble state, you can conclude that yes, that you find a certain frequency as the measurement outcome, but the conclusion that follows then, that each state in the ensemble should have certain probabilities, is one that is usually not compatible with quantum mechanics. It doesn't usually follow in quantum mechanics. So the question is, why should you take this as a meaningful explanation of the Born rule in the other situation? So yeah, that was that for today. To briefly summarize, the main takeaways for this lecture are that the measurement problem is not a purely philosophical problem about interpretations of the theory. It is an actual inconsistency of quantum mechanics in the way it is usually defined, it's usually taught, and there are these three statements that cannot all three be true. This is the no hidden variables assumption, the linear evolution of the Schrödinger equation, and the determinedness of measurement outcomes. So in order to resolve this inconsistency, you need to get rid of one of them, and based on that, you either end up with a hidden variable theory like Bohmian mechanics, or you end up with some nonlinear evolution like in collapse models, which we will talk about in the next lecture, or you will end up with some sort of many modes interpretation of the theory. Thank you for listening, and see you in